Hey, hi everyone. So let's discuss this additional example. So we have a given 1 kilomole of octane burned with 20 kilomoles of oxygen. Assuming the products contain only CO2, H2O, O2, and N2, determine the numbers of moles of each gas in the products and air fuel ratio in the combustion process. So we have a complete combustion in this scenario. So there are alternative ways to solve this, but I will just solve this the fastest way. So the fastest way to do this is just do the chemical balancing. So you have octane, which is C8 H18, okay, and then plus 20 kilomoles of O2. So basically O2 and oxygen, because we still have nitrogen in the products. No? So we have to include nitrogen in the air as well. No? And then you have the products of combustion, H2O, and then O2. Sorry, it should be X, Y, plus PA. So you have an excess oxygen, and then you have the inert nitrogen. So in here, what can we do is we can do the chemical balancing for the actual, no? So this is the actual, no? Actual combustion or the complete combustion. So in here, we can start with the carbon first. So the carbon is 8, no? So you can see for the hydrogen, we can see that this is 18 is equal to 2y. Therefore, this is y is equal to 9. So for the oxygen, you have 20 molecules times 2 and then equals 2. So for the carbon dioxide, you have 2 molecules. So you have 2x, no? Just write here the x already, since you already got the x, and then you have y. So y here is 9 for H2O, and then plus EA. Oh, so multiply. We forgot to multiply this by 2, so you have 2 EA. So we can solve directly the both the excess air and the theoretical air needed, no, or the theoretical air molecules needed. Instead of just finding E and A separately, so we can find EA, which is the coefficient of O2. So this will be equal to, so let me just figure this out. So you have 40 minus 16 minus 9 over 2. So EA, okay, let's check that out. So you have uh 40 minus 16 minus 9 over 2. So this will be 7.5. So we get the coefficient, we are good with that, no? And then for the nitrogen, we have 20 times 3.76 times 2. Actually, if you don't want to, you can omit the 2 since both has the 2. It will just cancel out. Uh, but anyways, so let me write this down. So this is 2z. So the z here will be equal to, so we just cancel the 2. So this will be just 20 times 3.76. So you have 75.2. So we already got the first question answered, no? So we have the molecules. So this is equal to x, 8. This is equal to 9. This is equal to 7.5. This is equal to 75.2. So we have the following coefficients for this complete combustion. Now the next part is to determine the air fuel ratio of this combustion process. So you can do the typical way of solving things. I will show you two alternative, the one that we actually use and an alternative way or an alternative method to solve for this. Though there will be discrepancy, and I will discuss later the discrepancy between the two alternatives. Or basically, we have the the one that we're used to, and we have the alternative. So the one that we're used to, we can find the air fuel ratio that is molal, wherein we just multiply this, no? So this one by 4.76, no? And then divided by 1. So this is 1 molecule of octane, so divided by 1. So you have here, I think this is 95.2. This is kilomole of kilomole of air per kilomole of fuel. Okay, and then what we do is we just say that the molecular weight of air is equal to 29, and then the molecular weight of the fuel, or I'll just write F here, is we have 12, or just 8 times 12, plus you have 18 times 1. So this will be 114, no? So this is in kilogram per kilomole, no? So kilogram per kilomole of air, this is kilogram per kilomole of fuel. So if we multiply this using unit analysis, we can say that the air-fuel ratio in the mass basis is 95.2 kilomole of air per kilomole of fuel multiplied by, so you can see here, this is 29 kilogram per kilomole of air, and then you have 114 kilogram per kilomole of fuel. So as we can see, we can cancel out this, cancel this. So what happens is we only have kilogram of air per kilogram of fuel. So the actual mass is, it's supposed to be 24.22. I won't use the calculator anymore. So we're good with this, no? But I just want to show you an alternative way to solving this. So actually, 29 is just an estimate molecular weight. The actual value is around 28.9, no, or 28.8 to around 28.9. So let me show you how to do this. So there will be a different answer here. And an alternative way to solve this is, since we know the number of moles, no, for the air, and also number of moles of the fuel, we can use their molecular weights, or the independent elements, the molecular weight of the independent elements, so that the mass, the air-fuel ratio will be just 20 kilomoles of air, or sorry, of oxygen, 20 kilomole of oxygen multiplied by its molecular weight. So the molecular weight of oxygen is 32. So 32 kilogram of oxygen per kilomole of oxygen, no? And then plus, so as you can see, if you can cancel this out. So you have here 20 kilomole of oxygen. We can cancel this. Actually, this is also oxygen. We can cancel this. We have kilogram of oxygen. So we can do this directly. We can find the direct weight of the molecules, no? And then plus you have 20 kilomole. So the other component is the nitrogen. So the nitrogen has 3.76 more kilomoles, or molecules of oxygen by volume versus, nitrogen has 3.76 more molecules than oxygen. And then multiply this. So we have to multiply this by 3.76, and then multiply this by the molecular weight of the nitrogen, which is 28. So you have 28 kilogram of nitrogen over kilomole of N2. So this will be in kilomole of N2, basically, no? So you can cancel this, or not really the 3.76, but this one, no? So what happens is this will be the kilogram of oxygen plus kilogram, so the total here, and nitrogen, which is basically just the kilogram of air, no? Basically everything here, no? So divide this by how many kilograms is the fuel. So you can imagine we just have 1 kilomole, no? 1 kilomole of the fuel, right? Because in the balance you have a coefficient of 1 there. And then multiply this by, so for the carbon you have 18, no? 8 only, 8 molecules of carbon. So 8, and then the molecular weight. So I'll just write this down. So 8 kilomoles again of carbon multiplied by its molecular weight, which is 12 kilogram of carbon per kilomole carbon, no? And then plus you have 18 molecules for octane of hydrogen, and then you multiply this by 1 kilogram of hydrogen per kilomole of hydrogen. So as you can see, you can solve this. Let me just try this one. So you have 20 times 32 plus 20 times 3.76 times 28. Yeah. Then you have 8, so I'll just omit the 1. 8 times 12 plus, so I will omit the 1, so plus 18. So you will have an answer of this, so 24.08. Okay, so 24.08 kilogram of air. So if you do the analysis, this will be just the kilogram of fuel. So this will be now the kilogram of carbon plus the kilogram of H2, which is basically just the mass of the fuel, no? So this will be per kilogram of fuel. So there is a discrepancy, of course, because again, this is just an estimation, no? This is what we've agreed on, but the actual molecular weight is around 28.8. So if you do this again, okay, let's try this again. The molecular weight, actually, the molecular weight of air can be also identified, no? Which is this. So you have 1 molecule of oxygen times 32 plus 3.76 molecules of nitrogen times 28. So this will be the total molecules. So you have to divide this. I forgot to divide this. So you have to divide this by the total number of molecules. So this will be the actual, no, molecular weight of air. No? And if you use this, no, as the molecular weight, so recalculating this again, you can have an answer here that is quite similar to what we have done. So you have 28.04. So anyways, regardless, you can use 29 or you can do the long method, no, or just use 28.8. It will be the same, but anyways, I've taught you so far that it should be 29 as an approximation. Okay, so that's all, and thank you guys for listening.